What am I not working on, and why? Let me start there. So one thing that I'm not working on, I'm not going to tell you about it today, is surrogate or reduced order modeling. So I'm going to talk about dimension reduction. I assume that some of you have some idea of what this curse of dimensionality is, and I'll talk a little bit more about that in a second to motivate sort of what I am working on. Oftentimes, reduced order models or cheaper surrogates or emulators, if you're in the computer experiments community, are touted as ways to fight the curse of dimensionality. That we'll take our expensive simulation like we saw in the last talk and we'll build some kind of cheap emulator which allows us to run many more of them more efficiently, more rapidly. The problem is if you just take your one simulation, you make it cheaper, you're not actually fighting the exponential increase in cost that's associated with the curse of dimensionality, unless you can find a way to exponentially decrease the cost of your simulation as your dimension increases, which is not what happens. You know, maybe we get 1/10 of the cost or even 1,000th of the cost from your emulator. But you're still going to run into this exponential increase in cost with the dimension. So surrogate modeling and reduced order modeling is not a cure for the curse of dimensionality. I'm also not going to talk about adaptivity or partitioning the parameter space. Some idea of saying in some region of the parameter space our function is more easy to emulate, so let's use less work there. And then in this region where it's more complicated, we'll use more work. Because again, with respect to dimensionality, as soon as you get into high dimensions, it's really hard to talk about partitioning the parameter space in a way that does not suffer from the curse of dimensionality, does not suffer from this exponential growth in the cost that it would take to actually do that partitioning. So these are not things I'm going to talk about. Instead, so let me motivate a little bit about what's going on in high dimensions, so then I can talk about dimension reduction. Right? So there is, of course, and many of you are in this room are more familiar with this than I am, the information-based complexity notion of tractability. This is one of my favorite books on this subject. It's very accessible, so those of you from the statistics community who might not be really familiar with this work of information-based complexity, I highly recommend that you get this book on complexity information by Traub and Warschultz, where the gist of the idea is it's a formal structure for setting up for understanding the cost of an algorithm and how much the cost of the optimal algorithm grows as, for example, the dimension increases for example, some kind of epsilon approximation. I would say that the criticism of it in practice is that it is highly formal, and it's often difficult to assess sort of those costs for the optimal algorithms for the problems that we want to solve in science and engineering. But nevertheless, I think that this perspective of information-based complexity is critical to understanding the difficulties that happen in high dimensions formally. Here's sort of another toy problem that people who study high dimensions often look at, which is the volume of a unit ball in m dimensions, which can be written as this formula of exponential of a constant pi divided by the gamma function with some term related to the dimension. And what I'm plotting here is this volume of the unit ball as a function of dimension. And the thing that's really interesting about this, and here is the exact same plot except on a logarithmic scale, is that the volume of the ball decreases exponentially with dimension. And I think that this has really important consequences for emulation based on Gaussian processes. Right? So if you're doing Gaussian processes and you say, you know, I believe that my function value here is related to my function value nearby, where nearby is some notion of like a unit ball's length away or maybe some scaled unit ball's length away related to something like a correlation length, this is going to kill you in high dimensions. There's no longer any notion of nearness because the volume of your ball decreases exponentially. So it's very difficult to talk about nearness in high dimensions. Here's another paper that I found recently from the theoretical database community, which was something I never expected to read. When is nearest neighbor meaningful? And this came out in 1999 in a conference called Database Theory. And they have a really interesting description here, where they say when you sort of plot things in a 2D plane and you have some set of points and then you have a query point, this notion of nearest neighbor sort of makes sense. It's meaningful in some sense. But let's say that your data was actually sort of around a circle, and then your query point is just off to the side of the circle. So here's your nearest neighbor, but there's the sense in which all of these are kind of near, right? And their point is that actually this is the situation that happens in high dimensions. And to see this, they do the following experiment, which I was able to replicate. Imagine taking a set of random points in the unit ball, 0, 1 ball, not ball, cube, the 0, 1 hypercube. take random points, pick a query point, and now compute the distance from that query point to its closest neighbor, and compute the distance from to the furthest point away from that same data set. Now take the ratio of those two distances. Now repeat that process over and over again for a bunch of different sample points and a bunch of different query points. And what I'm showing here is what happens to that expected ratio. That expected ratio, as dimension increases, converges very quickly to 1. Then this is for 10 points, 100 points, 1,000 points, 10,000 points, and 100,000 points. So even if you're growing your number of points in your high-dimensional space like this, the ratio of the distance between your nearest neighbor and your furthest neighbor gets to 1 very quickly. Which means there's no such thing as near in high dimensions. There's no such thing as nearest neighbors. This was a phrase that Brian Rich, as a statistician at NC State, told me that I think is a really interesting phrase, and this is finally something close to quantification of that phrase. However, they didn't do this in the paper, but I thought, but if the dimension increases, certainly, let's say the variance or the standard deviation of this ratio must increase also. So I plotted that also. So here's the standard deviation of this maximum distance over minimum distance for these query points of nearest neighbors. And this converges very quickly to 0.1, and I have no idea why. But notice that it converges something small. It doesn't blow up with dimension, which I thought, again, was really interesting. And I think it has really important consequences for emulating when you're based on radially symmetric kernels, such as in Gaussian processes. Okay. So those are the troubles in high dimensions, and so in my mind, the best way to fight the curse of dimensionality is to reduce the dimension. So let me say something really quickly about what I mean by dimension reduction. To be honest, I'm a little bit embarrassed that I have to say that, but every time that I write a paper about this type of dimension reduction, people compare it with methods from other types of dimension reductions, and I'm like, well, that's a different problem, so why would you even ask me to compare that? So let me go through this really quickly. And pardon the notation, it's just used as a cartoon. So let's say that we have some system that depends on S for space, depends on T for time, and depends on X for parameters. And from space, time, and parameters, we may have some kind of a solution to a PDE, or maybe a complex PDE system. And then let's say from that PDE solution, we want to pull out some functional of interest, some quantity of interest from that PDE solution. So what does dimension reduction mean in each of these contexts? So in space-time, this is the realm of classical physics and mechanics, right? Your system is steady, so you don't have to think about time. Your flow is dominantly in this direction, so you can reduce the dimension from 3 to 2, for example. In the parameter space, maybe there's some correlation structure in your parameters to your physical model, so you might do something like principal component analysis, Karin and Loew, or some kind of covariance-based reduction to find some uncorrelated set of parameters that replace this set of parameters. Or alternatively, if you're a physicist, maybe you do some kind of dimensional, or a mechanical engineer, you'll do some kind of dimensional analysis to find a set of underlying unitless variables or dimensionless variables from your system. If you want to reduce the dimension of your state space, this is the realm of model reduction, things like proper orthogonal decomposition or reduced basis or empirical interpolation. A really nice survey just came out, edited by Peter Benner and Albert Cohen and Mario Oberger and Karen Wilcox. Ron DeVore has a really nice chapter in it that just came out last year from SciAm. Okay, but here's how I want to think about the system. I want to think about the system, and this is going to be very comfortable for those of you from computer experiments and from UQ, as a map from my parameters to my functional of interest. And I want to ask, how can we exploit the map from the parameters to the quantity of interest to reduce the parameter space dimension? So not using covariance information. I'm just going to call this thing f of x, because that's what we called it in high school. And so I'm going to go ahead and assume that the parameters are independent. And so what I mean is that if there was correlation or covariance structure, I've gotten rid of it with something like PCA or Karin and Loew already. Okay? And I really want to exploit this map to do this dimension reduction. The idea of this has already come up in the last talk, sensitivity analysis, right? Like, let's see if I perturb these parameters a little bit, how much does my F change? So I'm not, global sensitivity analysis, sometimes a statistician call it variable screening, is coordinate based. It's saying of my vector of x's, which ones are important. So for me, what I'm going to do is I'm going to generalize that a little bit. Instead of saying which ones are important, I'm going to look for important directions in the space of the x's. Here's a slide really quickly, just summarizing some of the applications that I've worked on. I put this up here for two reasons. One, I'll just summarize and say things that happen in energy, things that happen in energy modeling, things that happen in aerospace, things that happen in environmental sciences, things that happen in mathematical biology. These are the kind of models that I work on. I put this up here to emphasize my values. Okay? For me, the values are in the science. For me, the reason to do dimension reduction is to help solve the science problems. While I also value the mathematics and the analysis, in the end, for me, what I want to do is help the scientists and engineers solve their science problems, not necessarily find a slightly better constant for some kind of an error-bound error analysis. Okay, so, and these pictures will come back in a minute. But let's say that we have our f of x within uncertainty quantification. Often the kinds of things that we want to compute are mathematical problems that often look like this. So some kind of an approximation, we want to build an emulator. Some kind of integration, we want to compute statistics. Maybe we want to do some optimization in a design context, or maybe something like inversion, that if you give me something about the outputs, then you ask me to find the inputs such that the inputs gone through that model are consistent with the given outputs. Okay, at a really high level. And again, these are the types of problems that when f is nonlinear and does not have any kind of structure suffer from the curse of dimensionality, because as the dimension of x increases, you have this higher dimensional space that you need to explore exhaustively to solve these kinds of problems. Okay, so there are lots of methods out there that exploit particular types of structure in that map from the inputs to the outputs. For example, if your function is nearly additive, or if its mixed partial derivatives are sufficiently small, then sparse grids work really well. High-dimensional model representation, things based on ANOVA decomposition. If you're integrating Latin hypercube, tends to work really well in this type of setting. If your function can be well represented by a sum of products of univariate functions, where the number of terms in this sum is relatively small, this is low-rank structure. Methods based on separation of variables, or tensor train, or adaptive cross-approximation, or proper generalized decomposition tend to work really well if you have this type of structure. If your function can be written in a series where many of the coefficients, in some basis, where many of the coefficients in this series are 0 or nearly 0, then techniques based on compressed sensing tend to work really well. Okay, but the question is, if I just give you a map from input parameters to output that comes from some science and engineering problem, how do you know that it satisfies any of these structures such that so you can decide from among the myriad methods that we've all developed to solve these kinds of high-dimensional problems? And I would argue that it's really difficult. So instead, I want to take a more exploratory perspective. So this is a perspective that comes from Tukey in exploratory data analysis. I'm quoting here from his book, Exploratory Data Analysis. The font choice is his. I am quoting the font choice. It is not mine. And he says, even more understanding is lost if we consider each thing we can do to data, and I would say model, only in terms of some set of very restrictive assumptions under which that thing is best possible. Assumptions we know we cannot check in practice. And so what I want to do is, as opposed to saying my function satisfies one of these, I want to be able to check for some kind of underlying low-dimensional exploitable structure. Nick Trefethen had a paper that came out in SciRev recently, Cubature Approximation Isotropy on the Hypercube, where he says many algorithms aim to diminish the curse of dimensionality. Such algorithms take advantage of special properties of the functions being treated, such as alignment with the axes, but their authors do not always emphasize this aspect of their methods. So again, I want, instead of saying I assume my function is this and now I do this to it, I want you to give me a function and be able to test for particular types of structure. And so this is the idea behind sort of looking for important dimensions with, say, active subspaces. So let me show you this 1-minute video that describes active subspaces in just 1 minute. And then you'll get the whole idea of the talk in just 1 minute. So imagine we have our function, our map from 2 inputs to 1 output of interest. We look at it from a top-down view. Let's sample this function randomly in its domain, and at each point we'll compute the gradient of that function, which is a vector in 2 space. I'll take that collection of gradient vectors, identify one relatively important direction, an orthogonal direction that's relatively less important. Now imagine rotating our perspective so that we see the variability of this function along this relatively important direction, and now I can do dimension reduction. Okay, so what I'll do is I'll pick a few points along this direction along which things are relatively important. I need to check to make sure that I got that direction right. So for each of these points, I'll go back and I'll do a few samples along the relatively unimportant direction. I'll collect those sets of samples associated with each of the points. Maybe you call it the design, if you'd like. And now from each of these sets of points, I'll do some averaging, and now I can connect the dots and build a 1-dimensional approximation of my 2-dimensional function. There's my approximation. Extend it into and out of the board, and now I have my 2-dimensional approximation that's really a 1-dimensional function. It's a function of one linear combination of those 2 original variables. And like, okay, so that's neat. So how does that happen in higher dimensions? So this is a really important plot for you to see the next set of slides. So I really want to go over this in some detail. These blue dots here represent 100 samples from an engine performance model that we're using in our DARPA project on nozzle modeling. What I'm plotting here is the one output of interest, which is efficiency, as a function of one linear combination of the corresponding 10-dimensional parameter samples. So there are 10 inputs, one output. This is just one linear combination of those inputs. Over here, the red dots are the weights of that linear combination. So if I have weights that are 1 and the rest that are zeros, then it's essentially a scatter plot of the output efficiency versus the corresponding sample of whatever that first variable is. Now, as I change these weights, lifting one up, moving one down, what you can think of is that we're rotating the domain of this function in 10 dimensions. And we only have point queries of this function. We can't actually see a surface. But this is like a shadow of a 10-dimensional surface. Into and out of the screen is a 9-dimensional subspace. The black dots identify the most important linear combination that we've found. And you'll see what happens when the red dots go to the black circles. All of a sudden, a whole lot of structure lines up in this particular function that they didn't know was there. Okay. The aerospace people that put this model together, they said this is a nonlinear model, and it's not very complicated to evaluate, but it turns out that it's very nearly linear as a function of one linear combination of these parameters, which ultimately means it's a linear function of the parameters. And these weights, none of them are really zero. There's a group that's relatively small, there's a couple that are relatively big, and you can use these weights as sensitivity metrics for understanding which of the parameters are important. Okay, so that's the type of structure that I'm looking for by finding these important directions in the parameter space. So again, my values arise or sort of drift toward the science and engineering problems. So this is my question. Do these structures arise in real models? Short answer is yes. Let me show you a bunch of examples. So here is a hypersonic scramjet where this is the exit pressure from this system, multi-physics, very complicated flow, combustion, all kinds of things, as a function of one linear combination of 7 environmental parameters. Here is the integrated jet nozzle model that we're working on as part of the DARPA project. 16 different outputs of interest as a function of 175 different parameters. 40 of them represent uncertainty, and the remainder represent the geometry configuration for this 3D model. Each of the linear combinations associated with each of these outputs is different, but you're looking into a 174-dimensional space. From an integrated hydrologic model, this is the heat that transfers from the subsurface through the surface into the atmosphere, affecting things like climate change, as a function of, in this case, it was 3 different parameters. In this case, it was 18 different model parameters in this environmental model. Aerospace geometries, this is a three-dimensional transonic wing with 60 different control parameters representing its geometry. This is drag, and this is lift from this system. These little shadows right here for the statisticians, this actually represents the results of a bootstrap analysis if we bootstrap what that important direction is. This is T-cell count from an in-host HIV model, dynamical system model. There are 21 different parameters representing sort of like rate coefficients in this dynamical system. Maximum power from a solar circuit model, a solar cell circuit model as a function of 5 different parameters in this circuit model. An atmospheric reentry vehicle, the stagnation heat flux and the stagnation pressure as a function of one linear combination each of 7 different environmental conditions that this reentry vehicle is going through. The average velocity and the induced magnetic field from a magnetohydrodynamics generator model as a function of 5 different physical parameters. Voltage and capacity from a lithium-ion battery model as a function of 18 different parameters in this lithium-ion battery model. Drag count from an actual Volkswagen Passat geometry as a function of 16 different parameters representing its geometry. This is for those of you that do parameterized PDEs. You can play with your sort of our standard elliptic problem. Whoops, that wasn't me.
Well, thanks for that talk.
Yeah, thanks. There it is. Okay. This is as a function of 100 parameters representing the KL expansion of your elliptic coefficients. But they're not in every model. And this is the thing I really like, again, about this type of structures we can check. Right? I don't have to tell you that it's in every model. Go out and develop algorithms for this kind of structure. Here's a subsurface hydrology problem in 3 dimensions where we're varying hydraulic conductivity. And this one actually looks pretty good for this case, but here in this particular case that the environmental scientists wanted to run, there's not that one-dimensional structure. Turns out there's three-dimensional structures in the space of a 100-dimensional parameter space. This is work with Drew Corey at Sandia with an acoustic scattering problem with Helmholtz. We're doing a 50-term KL expansion of the wave number. And again, as a function of one linear combination of the variables, the output of interest from the system was not nearly linear. So it's not in every model. And I cannot map physics to presence of structure as much as we want to. Okay? But what I can do is develop numerical methods that check for this type of structure, and then if that type of structure is there, then we can try to exploit it. All that data that I just showed you is available on GitHub, and you're welcome to it. Wow, I did not time this talk very well because there's about 5 minutes left, and we're just now getting to the math. I'll try to push through this, and we'll get as far as we can, and you tell me when to stop. How about that?
All right.
Okay. So this type of structure is represented by something like this, and these are called ridge functions, where my function of several variables can be written as some other function of a few linear combinations of the variables. This type of structure shows up across, that is not me, across mathematical and statistical sciences and different subfields. Here's a whole bunch of references that I'm happy to talk through with you. Alan Pincus wrote a book that wrote a monograph that came out a couple of years ago on ridge functions. So this structure shows up a lot, including recently within uncertainty quantification. You see structure like this, you can ask questions like, what is this matrix U, or what are these important directions? What is this function G? And then finally, how do you measure this approximation error? So let me first just talk about, and not just first, the only thing that I'll talk about, is how do you find these important directions? So let's say, this is related back to that 1-minute video, let's say we have a function that's differentiable, so we can compute its gradient vector, and we have some input density associated with, or density function or measure associated with our input variables. I'm going to compute the following matrix, which I'll take that gradient vector and take the outer product of the gradient with itself. That's a rank 1 matrix, but it depends on the inputs, and I want to get rid of my input dependence. So I'll average that matrix against the density function or take its expectation over the parameter space, which gives me something that's symmetric, positive, semi-definite, not necessarily rank 1, but I can now compute its eigenvalues and eigenvectors. This matrix shows up within statistical regression in the context of sufficient dimension reduction, within some ideas for dimension reduction in machine learning, and also within signal processing. You might think that this looks like the Fisher information matrix. However, it's really important to note that I'm differentiating with respect to the same variables that I'm averaging with respect to. So Mark Girolami once called this a Bayesian Fisher information matrix, and if you're statisticians, that's like a clash of worlds. But Van Trees was actually the one that calls this a Bayesian Fisher information matrix because you're integrating over the parameters of your standard Fisher information matrix. The thing that's really neat about this is that these eigenvalues can help measure this structure. So writing these eigenvalues as a Rayleigh quotient, what you can see, did I get it? Nope. Yeah, look at that. Yeah, there's something wrong with the projector. But the idea is that the eigenvalue can be written as the average squared directional derivative of the function along the corresponding eigenvector. So that means that if you have a null space to this matrix, then there are directions along which this function is entirely constant or flat. And those are the directions that we want to find and then basically ignore to do our dimension reduction. Yep. Cool.
You got like 1 minute.
Yep. So let's just skip. Doo-doo-doo.
Being generous, I'll give you 2.
Thanks. Appreciate that. Okay. So this is one idea for computing important directions. The interesting thing is that these eigenvalues actually measure the approximation error. So again, this is sort of checking if this structure is there without having to assume that it is, if we can estimate these eigenvalues, the eigenvalues associated with the inactive space. And this comes from the Poincaré inequality. And that's a Monte Carlo method to do it, and that's how many samples it takes. And then this is the problem that we're solving. And then here's another idea for finding important directions, which is let's just build an optimization problem. Let's take something like our root mean squared error or mean squared error and minimize it over all possible subspaces, which now our optimization space is the Grafton manifold of n-dimensional subspaces. So that's another idea for finding important directions. And then we can do this computationally with something like a discrete least squares. Within statistics, there's all kinds of methods for finding important directions that show up in the context of regression modeling, and this is often called sufficient dimension reduction. And I'm happy to talk to you about the comparisons between what I just showed you and sufficient dimension reduction. There are also other optimization techniques, for example, projection pursuit regression that you might have heard of. Why do I like ridge structures? Because it's exploitable, not just for dimension reduction and not just for cheap surrogates. It gives you insights into which variables are important, and also, like I mentioned, it's discoverable or checkable by looking at eigenvalues, by looking at some non-residual metrics, and then at least in 1 and 2D, we can make plots. We didn't even talk about inverse problems, but I wanted to put Yusuf's paper up here. So Yusuf worked on some likelihood-informed dimension reduction in the context of nonlinear inverse problems with TC. Yusuf and I were in talks with that. We're talking about that, while Tan Bui and I worked on accelerating Markov chain Monte Carlo with active subspaces. And all this is related also to what are called floppy models in physics in the context of calibration. So sorry I had to skip through the math. We're now at the point of questions. If you don't have any questions, I have a few that I think are really interesting, and you're welcome to ask me mine. Otherwise, I'm Paul Constantine from the University of Colorado. I wrote a book called Active Subspaces that came out a couple of years ago, and thank you very much for your time.
Questions for Paul?
Hey, I ended on time. Hey, Rob.
So, hi.
Good to see you.
Yeah, hi. Just to ask. So, I mean, it's very impressive, but
Thanks.
but you still have 27-dimensional space.
Yes.
That you're trying to find your active dimensions in.
Yep.
So you still, in order to find those active dimensions, have to somehow know your evaluate your function and gradient of your function.
Yes.
How do you?
So
Anyway, are you sure that those flat bits that you find out, those projections, aren't just errors from your model?
So let me first just agree with your question, that's a great question. That really, if what I'm purporting and what I'm promoting is not methods for saying here's how to do the algorithm to reduce the dimension, but here are methods to check whether or not you can do dimension reduction, then what we need is to be able to say, yes, I'm confident that I have found that dimension reduction space. And I think that is the most important part of saying these are tests. And being able to say, like, what is the cost of those tests? So information-based complexity comes into this also, which is to say, if you're a doctor and if you're a patient, you go to the doctor's office, maybe there's a really quick test to see if you have some kind of disease or something, but it's very unreliable. But maybe there's a more expensive test that's more reliable. And so this is the way that I think about these tests for dimension reduction. There are things that might be really expensive, where you have to estimate integrals, right? But maybe there are some other really quick and dirty ideas for testing if that structure is there. And if you find it, you're done. If you don't find it, it doesn't mean it's not there. It just means you haven't been able to show that it is there.
Just more concretely.
Yes.
There is a myriad of projections of 127 dimensions.
Yes.
And you're checking whether it's flat in those directions.
What? Yeah. So.
And, how many samples do you really need in order to be sure that you actually have checked all of those myriad of?
Yes. It depends. It depends on the metric that you're using to define important subspaces. So just like within global sensitivity analysis, there are dozens of global sensitivity metrics. Each of them measures some different characteristic of the map from the inputs to the outputs. What I've shown, unfortunately, very quickly, is about a dozen or so different definitions of important directions. And for each of those, you want to be able to check that you actually have found important directions for the characteristic that you want to measure with your function. How many samples do I need to estimate an integral? Right? This is a fundamental question in information-based complexity. I would say that this particular integral, if we use Monte Carlo, we're aided by a concentration of measure. So if that matrix C is actually low rank, then we don't need very many samples to reveal its dominant subspace, its dominant eigenspace. And not even low rank, but it's just if there's a gap in the spectrum, and that's what our analysis shows. That if there's a gap in the eigenvalues, yeah, Ron, I see you, just one second, then the Monte Carlo method for estimating this matrix from which we get estimates of our eigenpairs actually works surprisingly quickly. It's something that scales like the rank, as opposed to something that scales exponentially with the dimension.
So I know there's going to be questions. We're going to handle three, and then we'll break for lunch. So I'm going to go with yourself, and then Iliad and Michael, okay?
Yes, sir.
So mine is more of a comment
Thank you.
than a question. So you're dealing with ridge functions,
Mm-hmm.
and so this is your model class. usually we put conditions on U, sparsity conditions on U. If you put such sparsity conditions on U, then you can compute the Galfond width.
Okay, right. This is the paper with
Galfond
Alberio.
width tells you how many samples you have to make in order to recover elements in that class to a given accuracy.
Yes.
If you make sparsity assumptions on U,
Mm-hmm.
then you can enter into roughly compressed sensing,
Yep.
except that you have this outer function G.
Right.
But there are theorems
Yes.
in this case where you can say that independent somehow of the number of parameters or dimensions, there are theorems that will tell you
Yes.
how well
Yes. And
you can recover under assumptions on sparsity of U
yes.
and smoothness of G.
I agree with your comment, and a lot of those theorems show up in work by Fournacier, work by yourself with Albert Cohen and Xiaoying Sever, and also some work from Sebastian Meyer, who looked at the information-based complexity idea of uniform recovery of just one-dimensional ridge functions. And yes, I agree. Again, it's very difficult to check the assumptions of those theorems when someone gives me a new problem, right? So.
Well, another thing I didn't see in your formulation of the problem, whether you're given data or you get to query.
Yes,
That's a
and
big difference.
absolutely, absolutely. And typically we get to query it. Yeah, I'm typically
Query,
assuming that we're querying.
Then there are theorems that tell you where to query. And then you
Yes.
do a posteriori analysis to determine whether this model really fit.
I am not at all arguing that that theory does not exist. What I am possibly arguing is that it's difficult to connect that theory to real applications, in my experience, working with the applications that I've worked
I
on.
mean, you don't know where to query, or I mean,
Meaning that in order to take advantage of that theory and say, here's where I should query, I'm going to be a poet. You have to know something about that function that you're trying to recover, right? You have to know something about its smoothness. You have to know something about,
like, yeah.
or you have to know that that vector is sparse. What I didn't show with each of those plots is what the components of those vectors were. Sometimes they're sparse and sometimes they're not. It depends on the problem, and which again we can get from measuring it.
If you have no model for the function, then of course you can't say where to query. I mean, you have to begin with some model. There's no universal querying that'll handle any function that you possibly could see. You're making the assumption
agree.
that you have a ridge function.
I'm trying to test if I have a ridge function when you give me a function.
Okay, so
Yeah.
you can, I'm saying that there is a optimal querying if you assume sparsity for you.
Yes.
That is that these weights would decrease
Yeah.
in some fast way.
Yep.
And you do random sampling, basically. You take random samples.
Right. So I'll tell you that what we're working on right now is a combination of finding the directions while also sampling along the important directions based on a Lipschitz model. But the Lipschitz model is not based on a single Lipschitz constant, but on a Lipschitz matrix that shows up in the Lipschitz formulation. So that's I agree that theory is out there. So thank you for pointing that out. I appreciate it.
Ilya.
Okay, very short practical question, and it relates to your earlier discussion. How realistically, right? Of course, I realize your point about the fact that how many evaluations do I need to get an integral is an open question, and ill-defined one. But if I have, let's say, half dozen dimensions,
Okay.
Relatively small number of dimensions, but I still want to see whether really I can reduce this to one or two.
Yeah.
How many models or how many queries do I need to take realistically to test for this and then to convince myself that it's actually working?
Let me briefly answer a related question, which is the number of parameters in your problem is a very poor surrogate for complexity, right? So whether it's 6 or 60 or 600 or 6 million, you can potentially have very low dimensional subspace. Now the question is, can you find them in a 6 million dimensional space with the same work that it takes to check a 6 dimensional space, right? So I'll tell you the very first thing that I always do and that I actually did with about half of those examples that I showed, is I fit a linear model, I take the gradient of the linear model, and I normalize it to have unit norm, I use that as my important direction, and I make a plot. And that's the very first thing that I do, and I show that plot to the engineer, and I say, look at all this structure that you have in your problem that you probably didn't know was there because you've been trying to do coordinate-based analysis, but it turns out that really if you looked along one direction, you would have found it, that was not axis aligned, you would have found it much easier. So the first thing that I do, take something that's roughly 2 to 10 times the number of parameters. That's my first test. But again, sort of back to Rob's point, that's a very cheap test. I can do that very quickly and very cheaply, and it's also unreliable. If it shows me something, great. If it doesn't, then I could potentially have to do something that's much more expensive. And if we get to the point that actually computing that average of expectation of the outer product is some terrible integral and there's no structure that I can exploit in there, then I'm going to be subject to every kind of integration issue that shows up in high dimensions. And something that scales exponentially with, like the information-based complexity tells us. So it depends.
Yeah, so I mean, my comments, I guess, are how does both science and sequence fit into this? Because I'm used
Science
to
and secrecy?
Science and sequence. Because I'm used to the fact that, of course, a model has many outputs.
Oh, yeah.
Okay, and much information that's derived from them.
Yeah.
And so the point you started off with was saying that if you have many outputs, sort of many dimensions, almost everything you do is an extrapolation. The convex hull of what you're seeing is a tiny fraction of the space.
Sure.
Okay? So our statistical knowledge is that when we fit models, it's very easy to get good interpolation properties, but bad extrapolation properties.
Yes.
Yeah, okay?
Sure.
So the thing
I'm
that
with you.
controls that is the notion of, firstly, not overfitting.
Yes.
It's the overfit that creates that. And secondly, having a scientific understanding of, of what the driving effects are, the reasons that, we are seeing some of these effects. Yeah?
Okay.
Okay, so to me, the first step is scientifically understanding which things, which outputs we have observations on,
Yes.
and we have a reasonable scientific understanding for, doing those fits, passing them through the scientists, diagnostic testing on those,
Yes.
and using those to reduce the space.
Okay.
But a lot of the reasons that you can't fit the whole space are because you're fitting all sorts of different regimes, many of which are just physically, unrealistic given the world.
Yes.
And as you gradually reduce the space, then many more things fall into this thing. So I think there is a narrative that fits in. You have to make the problem, in a sense, bigger before you can actually address it and solve it.
Okay.
I don't know whether you...
Do you want me to comment on that? I mean, you're talking about a different problem.
No, it relates. No, I mean, essentially...
Or maybe I'm talking about a sub-problem of your problem.
Is that you kind of remove the science and the wider context.
Yes.
Therefore make it harder.
I agree.
That's my real comment.
Okay. Thank you for your comment.
All right, so we're 10 minutes over in terms of, I guess, lunch has started, if you will. Lunch is served, hopefully outside. So it's a buffet lunch. Those of you who have other questions for Paul, Paul's going to be here only till the end of the day, so track him down now, but I invite you to call him at his house, completely ignoring the time differences from wherever you happen to live. So, all right, so Paul, thank you once again.
Thanks.